In this video, we'll go over what happened when a cyclohexane's chair flip. So the cyclohexane chair can flip to produce two conformers. And here they are. And so basically the one on the left, we can see that their location, the position are different. So this one right here look to be this way, and the other one look to be opposite or flip. And these are the two chair conformations that we have learned how to draw already. So basically, whenever we have a chair conformation, it can flip back and forth between these two conformations right here, because they can have different energy or have different stability. So the ring can flip to produce a more stable conformation. And normally, this can happen up to 100,000 times per second. So that's the rate of flipping at room temperature right here. And in order for a chair to flip, then it actually requires energy. And on average, it takes about 10.8 kilocal per mole in order for one chair to flip to the other chair conformation. And the reason is because as it flips from one to the other, it has to go to the twisted bolt and the half bolt and so on before it can go from one chair to the other exact opposite chair conformation. Now, it's really important that we pay attention to what happened to the position on each of this carbon right here when the ring flips. And so here is how we'll be able to determine that. Now, so first let's label the carbon all the way to the left of the ring, being a carbon number 1. So in this case, this is the carbon 1, and this is carbon 2 and 3 and so on to carbon 6. And here on the when it flip, the carbon 1s end up being right here. So again, the carbon all the way to the left on left side, that remain to be the carbon number 1. So carbon 1 and carbon 1. Now, so let's see what happened right here to the position of the group. The blue bar here connecting the carbon 1. On the left side, on the left conformation, it is now pointing equatorial. So this is the equatorial position, and it is pointing up. So look what happened to it when it has flipped. So here, that blue bar, it is now remaining to be pointed up, except it now become an axial. So that's what happened to it right here. As the chair flipped, the positions remain to be on the same phase that they were initially in. So for example, if they were to be pointed up earlier, when they flip, it remained to be up. The only thing that changed about them is that they would change from equatorial into axial. So that is what happened to every groups connecting to the different carbon as the ring flip. For another example, if we were to be looking at the red bar connecting to the carbon 1, right now this is axial and it pointing down. So in the flip ring, this will remain to be down, but it will change from axial into equatorial. So that's what we would expect. So it will remain to be down, except this will now be changed into equatorial. So when we go here to the carbon 1 and the red bar, that is what we see. It's still pointing down with regard to the center of the ring, and in this case, it now becoming equatorial. And same thing to every group on every single one of this carbon. So here's what happened right here to summarize what happened when the ring flipped. When the ring flipped, the alpha group remain alpha. And again, alpha refer to all of the groups that are pointing up on the top part of the ring. So if they were to be on top of the ring, they remain to be on top of the ring. The only thing they changing is that they'll be changing from axial changing to equatorial. And equatorial will then change into axial. So that's what happened. And the beta group will then remain to be beta. And again, beta is another term for pointing down on the bottom, on the bottom of the ring. So group on the bottom will remain to be on the bottom, but they will change from equatorial into axial and axial into equatorial. So that's what happened. And now for an example, let's draw this ring right here. So first, let's draw two set of lines that are slanted. In this case, I'm slanting this to the right. So the top line should be to the left compared to the line from the bottom a little bit. And now I would imagine my horizontal line. I'm going to put a dot, and that way I put the first dot. And same thing over here. When we imagine this horizontal line, that way it would go. And now this is where I'm going to be putting the other dots. So those are the two dots that I would make, and I'm connecting this dot right here. And there you go. We will have that group. And now let's point out one group. Let's put one group in here, and let's see what happened to it when it flipped. So now here's what happened when it flipped. And we would draw this arrow to make sure it can be reversible. And now to draw the flip chair of this. Earlier we slanted this to the left, so now on the right side we should be slanted this to the right. And when we slanted this to the right, the top line will be shifted to the right compared to the bottom line. And again, I would imagine a horizontal line that go through this. And now I'm going to make in my first dot, that the dot right here. And same thing down here. Here will be that imaginary line right here. And now I'm going to make this dot. And now connecting the dot to the end of the line. And that's how we can draw the two flip chair. And in this case right here, this carbon would then be this carbon. So the carbon all the way to the right would then remain to be the carbon all the way to the right when the ring flip. So this carbon becoming this carbon. And as for the location over here, so let's call this group. So this group right now, it is pointing up and it is axial. So when it flip, it will then be pointed up still, except it changing to equatorial, right? So that's what we were expecting. So this will remain to be up and become equatorial. And now on this position, it is up and equatorial. So that's what happened to this group when it flipped. And now let's put in another group. And now let's change to blue. So let's say here will be the equatorial location. And right now, this is pointing down and it is equatorial. When this group flip, it should remain to be down, right? So when it remain to be down, and it will change from equatorial into axial. So what we will expect. And here we go. Here this carbon. Now it will be axial, and it now be pointing down. So that's what happened to every carbon when it flipped. And now let's do another example right here. So let's say here, let's put in another group. And now let's change this to green. So let's say here with this group. On this group right here, what happened to it when it flipped? So again, let's label our carbon. Normally by convention, we would label the carbon as follows: 1, 2, 3, 4, 5, and 6. And here should be 1, 2, 3, 4, 5, and 6. And again, for the carbon 1, since this is the carbon they pointed all the way to the left of in this conformation, when it flips, it will remain to be the carbon that is most shifted to the left as well. So that's how we can pay attention to it. And you can see right now this carbon right here pointing down. When it flips, it now become up. So that's what happened to every carbon when they flip. Up become down and down become up. So here in this case right here, this group right here in green that we're interested in will be located on carbon number 6, and that where that would be. So this green group right here, right now this is axial and it pointed up. So when it flip, it's supposed to become equatorial and still point up. And to draw it, this is how we would draw this. So here the carbon number 6, and again, to draw the equatorial for this group on this carbon number 6, it will be as follows. It has to be slanted to the right, and that way that would be. And now this is pointing up, so it point up with respect to the center of the ring, and it now becoming equatorial. And now let's also put in the equatorial position in here. So here it will be the other group. This will then be the group at the equatorial position. So as for this group right here, right now this is down, and it pointed and it is the equatorial position. So when it flip, this group in red, it will change, and it should now remain down and axial. So here go to this carbon 6, so this will remain to be down and axial. So that's how we can draw that group on carbon number 6. And let's do another example with carbon number 2. So let's put in a group on carbon number 2. So for this one, so let's say this one right now, this is axial, and it pointed up. So when it flip, this group number 2 should be now become an equatorial and remain to be up. So here in carbon number 2, so this would then be up, and therefore it have to be going in this way. So this is now up and becoming equatorial. Now as for the other position of this carbon number 2, since this is the axial location, the equatorial would be right here. And now carbon number 2, so when this group right here, since this group right here is equatorial and point down, when it flip, it will now become axial and point down. So here on the carbon number 2, axial and down. That way that will go. So make sure we know how to put in all of this group when the carbon flip from up and down. And perhaps maybe let's do the last example with carbon number 5. So here in this case, for carbon number 5, its equatorial location will be in this direction. And again, because this is on the right side, all of the equators will be pointing to the right. And here in this case, since this carbon right here is pointing down, so its equator will then be pointed up. And now, so let's group. So carbon number 5, when that group right there flip, it will change from, so it will remain to be up, except it change into axial. So in carbon number 5, that group right there in blue will now become still remain to be up, and it change from equatorial into the axial position. And the other one, so here will be the axial position on the carbon number 5. So this is now pointing down, so this is why the equator have to be pointing up in the first place. So here we get this is an axial position. So this position right here in red would now be remain to be down, and now it would then become equatorial. So there you go. So that what happened to every positions on every carbon when the ring flip. Now, the cyclohexanes and its chair conformation can also be viewed using the Newman projection as well. So sometimes being able to see the cyclohexane from the Newman projection can be valuable as well, so we can see the relative position of the group on them. And for an example, so when we view the chair cyclohexane using the Newman projection, again we need to figure out which bond to look through. In this case, let's look through this bond. And because these two lines right here are parallel, so essentially we'll be looking at these two bonds across. For the one on the right, so we would draw this, and that would be the front carbon, and we have this hydrogen, so let's HA, and that way HA would be. And the CS2 would then be pointed up to the right, to the left. So here, so right, so this is considered to be up. So there you go, from up, that way that will go. That's CS2. And there will be a hydrogen, and we call this HB, and now HB would then be down. So that will happen to the front carbon. On the back carbon, this hydrogen right here, they point then up, and this one right here, they're pointing down, and now there's a CS2 right here in the back, they're pointing down. So on the back carbon, so again, this circle represents the back carbon, we have a CS2 group, they're pointing down, and there it is. And again, we can imagine what happened to the other carbon when we look across this carbon-carbon bond, and this is what it would look like. And overall, this would then be the chair conformation of the cyclohexane using the Newman projections.